Today, we're going to tackle one of the absolute cornerstones of statistics, the idea of sampling distributions. This concept is basically the bridge that lets us take one small sample, just a tiny peek at the world, and make these incredibly accurate statements about the whole picture. Honestly, it's the secret sauce behind almost everything we do in data analysis.
So have you ever wondered about this? It seems kind of crazy, right? You see it on the news constantly. A poll of just 1,000, maybe 1,500 people, is somehow used to predict what an entire country is thinking. How on earth is that possible? Well, the answer isn't magic. It's math. And the key to unlocking that math is understanding what we're talking about today, the sampling distribution.
All right, so here's our game plan. First, we're going to get a handle on what a sampling distribution even is. Then, we'll dive into the three big ones you'll run into all the time. After that, we'll see how this whole idea helps us pick the right tools for the job, and we'll finish up with a key rule of the game that really makes the whole system click.
Okay, let's jump right in. The power of one sample. To really get this, you have to kind of shift your thinking. We're not just looking at individual bits of data anymore. We're looking at the results of entire samples.
So this right here, this is the central idea for our whole discussion. A sampling distribution isn't about the data inside one sample. No, it's this bigger, theoretical picture. It's the distribution of the results, like the mean or a proportion, from every single possible sample of the same size that you could ever dream of taking. So imagine you go out, grab 30 people, calculate their average height, and you write that number down. Now, imagine doing that again with a different 30 people, and again, for every possible combination. The list of all those averages, that's what creates the sampling distribution.
Let's make this feel a little more real. We'll start with something you've definitely seen in polls and surveys, proportions. In stats, we give the sample proportion a little nickname, p-hat. And it turns out p-hat has a really cool story to tell when you look at its distribution.
So sample proportions have these two amazing behaviors. First, if you were to plot the results from thousands of different samples, they almost always pile up into that classic, symmetric bell curve shape we call a normal distribution. And second, and this is huge, the very center of that bell curve will land exactly on the true proportion of the entire population. It's that predictability that makes this whole thing so incredibly powerful.
And this illustrates it perfectly. So think about the process. You grab a sample, you calculate its proportion. That's your p-hat. You do it again, you get a slightly different p-hat. You keep a list of all these different results, and then when you plot all of those results on a graph, they stack up to form that beautiful, predictable, bell-shaped distribution.
And here's that exact theory in action. The experiment couldn't be simpler. You roll a regular die 5 times, and you just count the proportion of odd numbers you get. Now we know the true proportion should be 0.5, right? 3 odd numbers out of 6. And look at this. After doing this 10,000 times, the distribution of all those sample proportions forms a nearly perfect bell curve, and it's centered precisely at 0.5. The theory just works.
So let's move on to our next type. We're going to apply the exact same logic, but this time, instead of proportions, we're looking at the average of averages, the distribution of sample means.
And you're probably not going to be shocked by what we find. Just like proportions, the distribution of sample means also tends to form a normal distribution. And crucially, the average of all of those sample means is equal to the true population average. See the pattern here? It's this powerful, predictable behavior all over again.
Let's go right back to our die rolling experiment for proof. This time, instead of calculating the proportion of odd numbers, we calculate the mean of the 5 rolls. After 10,000 trials, the histogram of all those sample means creates another fantastic bell curve. And where is it centered? Bam! Right on 3.5, which is the true theoretical average of a 6-sided die. It just works.
Okay, so we've seen that proportions and means behave in this really similar way. They both create these nice symmetric bell curves. But what about variance? You know, the measure of how spread out the data is. Well, this is where things get a little weird.
Here is the big difference. The sampling distribution of the variance is not a normal bell curve. It's actually skewed, with this long tail stretching out to the right. But, and this is really the important part, it still hits the target. On average, the sample variance will correctly estimate the true population variance.
And our trusty die roll simulation shows this clear as day. I mean, you can just see it. That shape is not symmetric at all. It's all bunched up on the left with that long tail on the right. But even with this funky shape, the average of all 10,000 of these sample variances is 2.9, which is exactly the true variance of the population. So different shape, but the same long-run accuracy.
You know, this whole idea that the center of these sampling distributions consistently lands on the true population value is unbelievably useful. It leads us right into the idea of estimators, which is just a fancy way of saying we're using a number from our sample to make an educated guess about the entire population.
And this table lays it all out. When a statistics sampling distribution is centered right on the true population value, we call it an unbiased estimator. As you can see, our friends, the sample proportion, the mean, and the variance are all in this group. They are reliable target hitters. On the other hand, statistics like the median or the range are what we call biased estimators, because, on average, they don't consistently target that true value. Now here's a really important little detail. You might notice the sample standard deviation is technically on that bias list, but in statistics, bias doesn't automatically mean bad or useless. The bias here is actually tiny, and it gets even smaller as your sample size gets bigger. So in the real world, the sample standard deviation is still the best tool we've got for estimating the population standard deviation.
Okay, one final, crucial piece of the puzzle. All of this powerful theory kind of depends on us following a specific rule when we collect our data. So let's talk about the rule of the game that makes all this beautiful math actually work.
So a lot of the theory we've been talking about assumes something called sampling with replacement. The idea is that after you pick someone for a sample, you theoretically put them back into the pool before you pick the next person. Now in the real world, we almost never do that, but it's okay, and here's why. When you're sampling from a massive population, like the entire US, taking one person out doesn't really change the odds for the next pick. So by treating our selections as independent, it makes the formulas and all the math behind the analysis way, way simpler.
So let's wrap this all up. The real magic isn't in the single poll you see on TV or the one lab experiment you run. The power comes from knowing the predictable shape that emerges when we imagine the results of all possible samples. We might only hold one little piece of the puzzle, but because of this theory, we know what the entire puzzle is supposed to look like. That's the whole secret of inferential statistics. And with that, we're at the end, but I want to leave you with this question to chew on. Now that you understand this kind of hidden architecture behind the stats you see every single day, from election polls to medical studies to the average rating on a product, what invisible distributions are you going to start seeing in the world around you?